Hi everyone. Thank you for sticking around. This will be the last talk of the day. And as I mentioned, after Rob's talk, you can go walk around the grounds or visit the bar, and we'll meet for dinner at 6:30. It's my pleasure to introduce Rob Lempert, who's visiting us from the Rand Graduate School, where he's a professor and also director of the Frederick S. Hardy Center for Longer Range Global Policy and the Future of Human Condition.
Great. Okay, good. So my talk, let me get, there we go. Okay. My talk's going to be a meditation on this adequacy for purpose argument, or a discussion that we've been having, mentioning a lot. And hopefully it's going to be a nice complement to a lot of what we've seen so far. I start with the famous all models are wrong, some are useful line, and lay out three more specific things that I'm going to discuss in this vein. The first two, I think I have a lot of substance to show you. The third is I'm mostly just going to imperfectly raise issues. And so, in part, if you think of a lot of examples in the history of science where first you figure out the practice and then you do the science. So maybe you regard the first two as examples of clunky steam engines, and then I'm going to lay out for you guys to figure out thermodynamics. There we go. So I'm going to alternate between sort of statement of concepts and principles and then examples. So let me start out with this basic, laying models into two classes, and this comes from a Rand colleague of mine, Steve Bankus. And so he distinguishes between consolidative models and exploratory models, and I think consolidative is meant somewhat as in the same way as we heard this morning. But a consolidative model is one that brings together all relevant knowledge into a single package, which can be a surrogate for the real world. It's often used for prediction, and sort of the canonical example is when you model an airplane in your computer simulation, you expect that what the computer simulation tells you in all relevant aspects is going to be the same thing as what the wind tunnel tests and the airplane flies. So it consolidates everything relevant you need to know. Steve introduced this concept of exploratory models, which are meant to map assumptions onto consequence, but not privileging any one set of assumptions. So they're just a map. They cannot be validated because you don't know which assumptions are true or not, but they can be useful in ways I'm going to describe. So let me lay out, I'm going to talk about decision-making, decision support. Let me lay out, again, some concepts here. So this idea of consolidative models are useful for what we often think of as the way we're going to use scientific information to inform decisions, which we put the label predict then act on. So what will future conditions be? So we spend a lot of time trying to understand what we know about the future, and the most formal way to describe that is a joint probability distribution over future states of the world. Once we know that, then we can rank decision options, generally through, again, formal way is some sort of expected value criterion, and then we maybe do some sensitivity analysis. This traditional approach works really well under a variety of conditions. Future isn't changing fast, it's hard to predict, not too much disagreement. And again, I always say that you would never get on an airplane where the people who built it and flew it didn't work really well in this predict then act regime. But this sort of approach can run into problems when you're faced with deep uncertainty. I'll define that in a slide or two. And there's a real pressure to underestimate the uncertainties because you don't want to be the one who says, oh, we can't do this analysis because we really don't know. Or you do the sensitivity analysis, and you can rank, you can come up with arbitrary orderings depending on what you assume of strategies. This idea that PD analyses can lead to gridlock, which we see all the time in climate, but if a policy recommendation is predicated on a forecast, and if you don't like the policy recommendation, you can attack the forecast, which may be a lot more vulnerable to attack than the policy recommendation. And this idea that we often know a lot about a problem that can help us order strategies, but which is not necessarily predictive. And here's a definition. Definition we use of deep uncertainty down at the bottom occurs when parties to a decision do not know or do not agree on the likelihood of alternative futures or how actions related to consequence. So it's basically, the probabilities are uncertain and the model may be uncertain. And it's just one example, very relevant to this group. I just stick this chart up from the latest IPCC report, and this shows precipitation forecasts from the model ensembles, and the hatching is where essentially the difference between the models is large compared to the signal. Yeah.
How do you distinguish that from any kind of uncertainty, any kind of decision-making thing that's going on? What circumstances?
We generally stick it on a continuum where well-characterized uncertainty is when you have high confidence in a probabilistic description.
Yeah, but outside of a casino, where does that exist?
Many frequentist sort of things. I mean, I think when you build an airplane, most of the things that you work on the airplane, you have pretty high confidence, you understand the failure rates, that sort of thing. Yeah. But, let me get towards the end. I have a little cube where I think it's better to talk about what style of analytics do you want to use to inform decisions, one of the criteria is the level of the uncertainty, but it crosses with other characteristics of the problem. So we could return to that at the end.
But just to understand, so that when everyone pretty much agrees on the probabilities, that's what you mean by uncertainty, and when people have different probabilities or don't think there is a probability, that's deep uncertainty?
Yeah. Though they may be wrong in their confidence, but yes. Okay, so the general way that we work with deeply uncertain problems is to, in some sense, turn the analysis around, run it backwards. So you start with a strategy or strategies. You use your analytics to ask important questions about the strategy. For instance, I've got a strategy, it's got goals. Under what future conditions does the strategy meet its goals and what does it not? From that sort of information, we can think about, say, modifying the strategy. How would you modify the strategy to make it less vulnerable to those futures where it doesn't meet its goals? And then you can begin to adjudicate trade-offs, okay? And I'm going to walk you through some examples to show you what that looks like in practice. So the first example I'm going to show you is for the Metropolitan Water District of Southern California. That little blue dot sort of up right in the center there is where Santa Monica, where Rand is. I think this works. I don't know if I have a laser pointer here. Oh, maybe there, yeah. Right, yeah, so Rand is right there. This services about 20 million people, a significant fraction of the US economy. Met runs the importation of water into Southern California, which provides about a third of the water for Southern California. Like most big agencies in the arid American West, they produce multi-decadal plans. In Met's case, every 25 years. They update it about every 5 years. So for their 2010 plan, it's called an Integrated Resources Plan, IRP. It describes a 25-year investment policy. They worried a lot about uncertainty, so they put in a 10% safety factor buffer and talked qualitatively about an adaptive management plan. We worked with them on that, and then after they had published this plan, we helped them think a little bit more systematically about what adaptive management meant. So we took their planning models, we ran them over many thousands of futures, we ran a cluster analysis to summarize those futures where the plan meets its reliability goals and where it doesn't, and we use that as a way to suggest early warning signs that they may need to adapt the plan. So let me take you through that. So what we do is we've got the model of their system, which is essentially a big plumbing model, a system model. We take a plan, and then we take an ensemble of climate models. I show you them here. They're part chosen for convenience and part because of historical legitimacy. The state of California used some of these, so it's easy for Met to use them in their plans. We stick them in the model, and so given one of these climate futures, given the plan, and given this system model, which is fairly high confidence, you can calculate the system reliability, okay? And then what we do is we do that for then the full set of climate projections crossed with different regional patterns of development and a whole bunch of assumptions about how hard or easy it is to implement different parts of their plan. And this is just a plot to show that there's a great big database of runs. A red dot is a future where the plan does not meet its goals. A gray dot is where it is. Okay, and then what do you do to make sense of this so that decision makers can use it? Is we essentially run classification algorithms against the big database and ask what is the best description of factors which separates the cases, the futures where the plan works, where it doesn't. And here you get something like this, where not too surprisingly, it's crossed between supply and demand. Demand these are a couple of different growth scenarios, and supply is weighted 90% pretty much on the change in precipitation, and about 10% on the ability of their groundwater projects to produce the yield that they're supposed to yield. Okay, so there's their planning assumption, and not surprisingly, it works. There's their vulnerable scenario. And this thing then is an artifact that the technical staff of the agency can use with the board, and they can basically follow this dot around and use it as, and they can extract early warning signs from this about when the plan is going awry or not. And I put the little note down here. This is the range of the climate model forecasts. And where this line is essentially high confidence, even if we don't know what which of the climate forecasts are right or not. And I just put the little note here is that in the last, this is a 30-year average, but the year to date we're down 40%. So there's a question of where we are on this thing. But we love this quote because I think it really kind of captures what we're trying to do with this sort of analysis. We're trying to provide confidence in plans, not the models. So one of the chief analysts we're working here with at Metropolitan, at one of these many stakeholder workshops they run, someone asks, do you really believe those climate models? And this, of course, is not a scientific question. This is a politically loaded question. And he answers, he didn't necessarily trust the climate models, but once they got through the analysis that produced their plan, they were going to have confidence in their contingency plans. Okay, so we're trying to move the locus of confidence, not necessarily the scientific information, which is deeply uncertain, but to the plan. Okay, so let me now go through these pieces, kind of pull them apart a little bit. I want to talk about this concept of exploratory modeling, and I'm going to give you, for that, an example of some work we did for the Port of Los Angeles looking at extreme sea level rise, and I chose this example because we're really sort of pushing out at the edges of what the science can tell us. I'm going to get to this, then talk about using these ideas for deliberation for wicked problems, and talk about a big effort we did facilitating the Bureau of Reclamation on planning for the Colorado Basin, and then open it up to what I think are some questions that are raised by this style of analysis. Okay, so this is pulling apart a little bit the slide I showed you at the beginning. What can you do with a bad model? Traditionally, we think models are meant to be consolidated, bring together all the relevant facts in a single package, validate the model, and then use it as a surrogate for the real world. And so we make predictions, and we predict, and then we can act. Okay, but in many cases, you can't validate it. Models, there's missing data, theory, and sometimes the future is just unavoidably unpredictive. And we spend a lot of time talking about climate models here, but I often use the line with the water agencies who are doubting their 30-year climate projections, and they are now, if you look at what their economic and development projections, particularly in sort of these areas of California that got hit by the recession, I mean, their economic models are much worse than their climate models, but they plan with the economic models. Anyway, but you can make valid arguments with unvalidatable models. And what one does is this exploratory modeling idea is that you regard a run of the model as a computational experiment, and a computational experiment is a model run that has potential to surprise you. And this basically, is the notion that we know a lot of, point by causal facts, but people lose the causal chain for situations that are unfamiliar. There's wonderful studies where they took Nobel laureate economists and they give them, a real case example of a country, and even they, if the causal chain gets more than 3 or 4 or 5 steps, they lose it in their heads. And they need some sort of tool, maybe pencil and paper in that case. But people lose causal chains, so I can know a lot of things about the steps in the chain, but the model can still surprise me. So a computational experiment is any model run that might be able to surprise you. An exploratory model maps consequences of one set of assumptions about the world, and then this approach of exploratory modeling is we're going to scan in a careful, designed way over many assumptions, map assumptions to consequence in a way such that we can draw valid conclusions. What kind of conclusions can you draw? One can reason from special cases, so existence proofs, identify bounding cases, surprises, previously unknown worst cases. So you can say, you can discover a way that something works. Generate hypotheses. You can come up with a hypothesis that, gee, if we face this sort of sea level rise, this sort of strategy might be appropriate, and then we can look across an entire ensemble. In this case, it's the climate model, but also the socioeconomic assumptions, and test that the strategy. See if that strategy indeed is robust overall, all the possible assumptions, or understand the types of cases where it might not work. Okay, so I'm going to focus on this in the next example. So, question, should the Port of Los Angeles harden its terminals against extreme sea level rise at the next upgrade? So these are these big container ship terminals. They're very high above the water. Every n decades, where n has been on the order about 1 or 2, they rip these things down and rebuild them. And so when you rip them down and rebuild them, it's very inexpensive to harden it against extreme sea level rise. But if you need to upgrade them in between maintenance periods, it's very expensive. So, yes, hardening at the next upgrade is much less costly. So let's be safe. Now, the insurance is not worth it. Okay, so how do you adjudicate that sort of argument? Okay, so in this case, we're going to work on a simple, benefit cost framework, looking at net present value, which seems to be appropriate in this case. So discounted benefit is the avoided cost, and the cost is the cost of the upgrade, and the avoided cost is 0 if there is no extreme sea level rise, and very high if there is. Okay, so that's fine. How do we calculate those things? You can put together a simple model, and this is actually just an Excel model that we did this in. Here's the vulnerability, which is lifetime of the terminal and level of flooding that triggers a reactive response, and the hazard is how fast the seas rise and when, and then the increase in any change in storm surge frequency. And if you know all those things, we can calculate the net present value of hardening at the next upgrade. Okay. The problem is, of course, we don't know all those things. And so here I list out all the parameters in this model, and the ones that are in red are deeply uncertain. This kind of goes to your question of what we're regarding as deeply uncertain or not. So we're taking the normal rate of sea level rise to be well characterized by joint probability distribution, which we fit to the past sea level rise in the area. Then these parameters having to do with abrupt sea level rise, which essentially has to do with disintegration of the ice sheets and rapid melt, mostly disintegration of the ice sheets, and increased storminess, and which we just have an extreme value distribution, which we actually have 80 years hourly data for the water outside the port. So we've got a good distribution for the past, and we just stretch it. And then key future terminal management parameters, and these things we assume are known at the time of the decision. Okay, so for the deeply uncertain parameters, we just scan over a wide range. And so what we do is we do an experimental design of 500 futures. Is just a Latin hypercube statistical design, which is just meant to be a good sample over the input space. We can calculate the NPV in each of 500 futures. I'll get to the deliberation part more in a bit, but the idea is that everybody's expectations are included in this ensemble. We then lay out the cases. So it turns out that, if this is 0, so here you're best to be reactive, here you're best to harden. So this thing, mostly you don't harden, but it's got this long tail. Okay, so the first question you ask is, what conditions put you in the tail? Okay, so again, this is all still high confidence stuff, because we haven't gotten to any of the deeply uncertain things. So we can run this cluster analysis against the cases in the tail, say what assumptions best distinguish the cases which are in the tail, which of those are not, and you get an answer that looks like this. So these are the parameters for extreme sea level rise. This is a terminal lifetime, and this is the change in the frequency of the extreme storm events. And basically, if you're at the high end of extreme sea level rise, none of this is particularly surprising, the terminal lasts a long time, and you get any change at all in the level of storminess. If all three of these things hold, then you're in the tail, and if not, you're not. So if we can call this a scenario, and if you're in this, if you think this scenario is sufficiently likely, you should upgrade, harden at the next upgrade. Oh, and then one other thing, which is particularly important later, is this cluster algorithm gives us measures of merit for the scenario. So we can say why we've chosen this scenario, and say in a contentious stakeholder group, there is a clear audit trail on why it's this scenario as opposed to some other scenario. Okay, so let me focus on this one, and we say, what evidence do we have going through each of these that this is something we might want to worry about? So this is the one that we have the most scientific information we can lay against it. And so this is work I did with Klaus Keller, which he was mentioned on a previous slide. I think I zipped by it then. But essentially we took two bounding analyses, and these are based on estimates as sort of the physical limits on how fast the ice sheets can fracture and melt. And this one by Pfeffer et al. Had a low, high, and a mid, so we fit a beta distribution to that. This is the state of California came up with this one, and so this is just a low and a high, so we just fit a uniform distribution to that. Then we have a simple model of the ice sheets, which we start with the uniform distribution on these parameters. We do a rejection sampling. We get a set of cases here, and we adjust the distributions on C and T to fit these distributions, and that gives us estimates for the probability distribution of those things, so we're basically fitting to the bounding cases. And it turns out with these very different cases, you pretty much always get the same answer. It's very close, but you get that the probability of this being true is no more than about 16%. Okay? And from that, then we can come up with conditions on the other two, the terminal lifetime and the increase in storminess. And it turns out, and this is for different facilities, so just kind of pay attention. And this is the imprecision in the sea level rise estimate. But basically, if you're in the blue region, and this is the probability that the terminal lifetime is greater than 50 years, and this is the probability that the storminess increases by more than the factor we showed. If you're in this region, you should harden at the next upgrade. It passes a cost-benefit test. If not, you're not. And it turns out these are really high probabilities for these particular two factors. I mean, there's really no evidence at all that would suggest that that thing is true. So we can say with pretty high confidence, even in this world of uncertainty, that you probably shouldn't harden at the next upgrade. We then repeated this for a whole bunch of 4 different facilities at the port, and for 3 of them, you're way past. You can say with high confidence you don't want to harden. 1, it starts to get a little bit more murky, and you might want to burrow down or think about if there's much cheaper ways that you could harden to make things clear. So this then is an example of how with by this backwards analysis, basically come up with vulnerability thresholds, laying it against the science, you can come up with some fairly strong conclusions even in this world of deep uncertainty. Just a couple of quick points, and going to the next example. I'm laying this against the IPCC approach for communicating uncertainty. The IPCC and the AR5 had an uncertainty guidance where they wanted to formalize the way of thinking about second-order probabilities, and so they came up with this level of confidence, which they broke down to evidence and agreement. So this is strong evidence, limited evidence, low agreement, high agreement. So if you're up in this corner with high agreement and strong evidence, you can reliably stick probabilities on your uncertainty. These other regions you can't. And this just shows that in the analysis I just showed you, the things that we have low confidence in are the ones that were most important to the decision. Okay, some quick thoughts on probabilities. This approach, I mean, there's this disconnect between the idea of scenarios and the idea of probabilities, because cognitively, one of the things that scenarios do for you is allow people to expand the range. Use scenario and analysis people. It expands the range of futures that they're going to look at, and because you regard the scenarios as plausible as opposed to probable, it allows them to consider the implications of the scenarios, even if they're going to be ineffective. And this whole polar thing, had we come in to the port engineers and said, oh, we've got a probability of extreme sea level rise, and we're going to look to see how that affects your facilities, the first thing they would have said was they would have spent a lot of time attacking these mushy estimates as opposed to thinking about the vulnerability or not of their infrastructure. So placing probabilities on scenarios can disrupt the sense of plausibility. So how to use scenarios for decision making? The solution that I showed you is to identify probability thresholds for scenarios, to come up with the scenarios, speak about them in terms of plausibility, identify probability thresholds that would indicate a need to change action, and talk about them in that way. Just so I stick at least one equation in, just to go through that in a little bit more detail. The key then concept here is that we're considering second order uncertainty essentially as imprecise probabilities or sets of probabilities, and so there's a little bit of a snarky slide, but you can calculate the expected value as the probability distribution times the consequence of choosing action S and getting future X. And so the things that are hard is choosing the set of strategies to consider, what futures to consider, calculating the performance of the strategy in some future X. These are all things, if you're doing this for a real client, take forever. And then a key one is knowing and convincing other people that you know the true probability distribution. But once you've set up this machinery, it's pretty trivially easy just to crank it through for arbitrary distributions. So we use lots of different probability distributions in these analyses. So probability can be an uncertainty as well as the state of nature. So let me talk about multiple objectives. So multi-attribute decision theory, the analysis I just showed you had a single objective, just cost-benefit. In general, you have multiple objectives. And so there's multi-attribute decision theories, offers this concept of Pareto optimal surfaces. So here, this is for a water agency analysis, but we have reliability and costs. Ideally, you would like, perfect reliability for low cost, but you can't have that. So this is a calculation of the trade-off space of options, and this is a Pareto optimal surface because you can't improve one attribute without degrading the other. And so, everything in here is dominated, and so you show this to people and they can decide where they want to be on the surface. Okay, so this is a standard way of doing multi-attribute decision analysis. So this is a cool slide here but with my colleague Pat Reed. So he's got these cool algorithms, just to show you that there are some fancy stuff behind this. And so the idea here is, in general, in many dimensions, you can find these surfaces, and Pat's got a particular set of algorithms for finding that. So the gray is this actual surface. The red are the cases that these algorithms find, and they both try to find on the surface and distribute themselves equally around it. And so if I can visualize that, that becomes useful. So then this is a case we went through for a Texas water utility, and this is probably way too complicated to actually show people, so we're working on getting it simpler. But the point here is we generalize this idea of Pareto optimal surfaces to the idea of Pareto satisficing surfaces. So this is the surface that doesn't move around too much as you scan through the deep uncertainties. So essentially what we did here is we had a number of, there's a Texas water utility. The question is, how did they design a water market? And there's a number of uncertainties. So we scan over some of the state of the world uncertainties, and we scan over a wide range of probability distribution, essentially weights in the tails of extreme drought, that sort of thing. And these are a bunch of solutions which are all on this Pareto optimal surface in this space of different attributes. The key thing here is that we've color-coded them, and the ones in the light blue are ones that don't move around much as you go through this deep uncertainty space. The red ones that move a lot. And you actually get a massively simple story out of this complicated picture, which is we looked at markets with different degrees of freedom, and it turns out that the simple markets, which are not, well, if you have a very complicated market, you can optimize it for very well. If you know the future is well characterized, the uncertainty is well characterized, I can choose a well-hedged market, which performs really well. But once the future starts to become deeply uncertain, the complicated markets fail miserably, and the simple markets actually work much better. That is, their performance is pretty stable as you vary the weights and the tails of the distributions by an order of magnitude. So that may even have broader applicability. But in any event, you can get strong, again, confident messages even from scan when the uncertainties are pretty deep. Okay, so let me go to this idea of wicked problems. So a wicked problem is one that's not well bounded, framed differently by various groups and individuals, involves large scientific uncertainties, and we really don't understand it until after the formulation of a solution. That's really another way of saying that the successful solution fundamentally frames the problem. And these problems are often very difficult to get at with analytics. In fact, there's this whole body of literature says, well, gee, quantitative analysis may in fact be useless for these sorts of problems. This is uncertainty over objectives, uncertainty over consequences. So if those both uncertainties are both low, you can use quantitative policy analysis. But if they're high, all we're left with is inspiration. And so that's a little bit unsatisfying. So the argument here is, in fact, we can do a lot better than that. So the example I want to show you of a real-life analysis on a wicked problem is some work we did with the U.S. Bureau of Reclamation on their most recent management plan for the Colorado River Basin. So here is the basin, 7 states plus Mexico. This is like 40 million people and a significant fraction of U.S. agriculture, U.S. economy is a very significant system. The challenge is that the river was allocated in the early 1920s at the high water mark of the millennium, which didn't matter so much because there weren't very many people in the American West. They all lived in California, not any place else. And so California could buy all the excess water allocated to the other states, and that is no longer the case. So the demand has crossed supply, and oh, by the way, the supply may be dropping. So they've got a major problem. So this was a study that the Bureau, essentially, the beginning of the renegotiation of the Colorado Compact. So we looked at 50 years, assessed supply and demand imbalances, developed a first cut at opportunities resolving this. And this, was a high-level study, and we were the facilitators of it, analytic facilitators, and this was released, the cabinet member, the U.S. Secretary of the Interior, released the work I'm going to show you. Okay, so again, let me lay out some concepts. Let me talk about this idea of decision support, which is sort of a collection of a body of information, cognitive, behavioral, analytic thinking about how you insert information into decision processes. So this is this Serowitz and Pelkey idea of the supply and demand of science. So this is, is the what information is produced? Can the user benefit from research? And you'd kind of like to be in this box down here. And the idea of decision support really adds this notion that the process by which the information is produced and meshed into the decision process can be as important as the information products themselves. So you need to pay a lot of attention to process. So I'm going to pay particular attention to this learning idea. And much of the work in this example is organized around this deliberation with analysis idea, which the parties to the decision, imagine a room full of people around a table, they define objectives, options, and other parameters important to them. That then feeds into the analysis, and you generate decision-relevant information, and then you feed it back into deliberations, and you go back around and around. And this particularly complicated and difficult, time-consuming process for feeding information, coupling analytics and decision-making, is useful when there's a lot of uncertainty and participants' goals and options evolve through interactions with others. So basically, your decision, your menu of options and your values are emergent from the process. Okay, so this is the way we organize our backwards analysis, our RDM analysis in this deliberation with analysis idea. First, there's a participatory scoping that defines a model and as experimental design. We run many thousands to millions of cases. We do the scenario discovery that I showed you. And then we generally feed back to new options and then do trade-off analyses, which hopefully lead to robust strategies. So going back to this little picture here, that loop, RDM loop, lays out on this deliberation with analysis. So you start with proposed policies and goals. That's a deliberation step. Identify futures where policy fails to meet its goals. That's an analysis step. Suggest policies that may address these vulnerabilities. Can be both analytics and deliberation, but there certainly needs to be an acceptance of the options by the group. And then you can identify key trade-offs among the policies. Then people can propose another policy, and then you can go back to the beginning, and you iterate through this. Okay, and this process can prove intensive. These are two of my colleagues that performed the Colorado work. This is a group of stakeholders. So this is actually a different group of stakeholders. This is actually the Louisiana Master Plan for Sustainable Coasts. So these are representatives of various parishes in Louisiana, but the same sort of thing we did for Colorado. Two key ideas here. One is these are all technical representatives of political agencies. Okay, so there's a question who's at the table, and these are highly skilled people coming in with agendas, but also, sort of professional need to solve the problem. And you meet with them, up to dozens of times. You meet every month for a year or two, that sort of thing. So this can be a very intensive process. Okay, we often organize these analyses into these 4 factors, which turn out to be a really nice way to parse up information and factors relevant to these sorts of decision exercises, and we call it XLRM. So, what are decision makers trying to achieve? Those are your goals. What might you do to achieve your goals? What uncertain factors outside your control affect the ability of your actions to reach their goals, actions to consequences, and then your system model, your models which relate, a lever and an uncertainty to your goals. Okay, and then once you've organized your information like this, you can start running the cases and do the analysis we described. Okay, so this is what it looked like in the Colorado Basin. Definitely a multi-attribute problem. If you count those up, there should be 26 different metrics of interest. A whole bunch of supply options. I'll talk about that a little bit. Again, using the legacy model that the Bureau of Reclamation has to run the system. Looked at some demand conditions, different ways that the system might be operated, particularly if it moves into crisis. But the thing I want to just focus on real quickly here is we looked at a lot of different climate projections. We just took the observed historical 100-year historical record, ran it forward, and various, created 103 traces based on the statistics of the 100-year historical record. We created traces based on the paleo droughts, the droughts of record over the last 1,000 years, which are a lot worse than the last 100. We used downscale GCM projections, and then paleo, a combination of those two become the paleo conditions. So the point here is that there's lots and lots of different projections.
What do you mean by trace?
Oh, that's just one projection into the future, yeah. And then we run a trace through the river system model. Traces, it's basically the daily climate for 50 years. You run it through and you see whether LA, Las Vegas, and whoever runs out of water or not. Contingent on all the other assumptions. So, and these were chosen in large part because different stakeholders would come and they had different questions. So it's like, well, I like the models. I don't believe the historic record. Some people like the historic record. Some people were worried about the paleo history. So this is basically meant to be inclusive. So we run that all through the system. This is a quick vulnerability map. These are different places on the river where people are worried about water supply, water reliability, and this just counts the number of traces. This is a set of about 25,000 different futures we're running. Each future is a climate trace, assumption about demand, and assumption about river management. And the point here is just that, particularly downriver, in virtually all the futures, by the time you get 50 years out, the system is failing. So we can do this vulnerability analysis on it and say, under what conditions does the system fail? So for one of those 26 measures, we run the cluster analysis. These are the climate projections, and then you find, of all the dimensions that are potentially relevant, it turns out change in temperature from historical and change in precipitation compared to historical, at least for this measure, are the most important for this policy. And so it turns out that what we show here is the gray are cases where the system meets its goal, the red X's are where they don't, and the best fit to that is essentially anything above 2 degrees Fahrenheit, and any change in precipitation, any decrease in precipitation, the system fails. Okay, so again, a contentious group who obviously recognize the consequences of writing in an official government document that the system is at risk, okay, affects their property values, affects all sorts of stuff. They have a lot to argue about, but this is a high confidence thing you can say, okay? All right, so what do you do with that? One thing we did with this is use scenarios to identify actions and signposts for adaptive plans. So we start thinking of a plan as an explicit contingency plan, near-term actions. We monitor, and here we're only monitoring average stream flow. And depending on what you see, you respond in different ways. Essentially what we do is we take for each of those 24,000, we've got 100 or so different policies, options in the portfolio, and we do an optimization for each 24,000 of these things and come up with the optimum adaptive plan for each one of them, and then we look at the commonalities among the plan, and this aims to summarize this. So here are a whole bunch of different actions you can take to reduce the vulnerabilities. We have 3 columns. This is all the traces for all 24,000 paths in the future. Here are 2 different clusters which are particularly important for this class of responses, and the names are convey as much information as we need to right now. But the number here is the number of traces, the percentage of traces in which you do this action. Okay, so for agricultural conservation, no matter what the future holds, you always do it. Okay, the size of the box is, do you do it now or do you do it later? Because this thing optimizes on when, for each trace, where it comes in. So you see different classes. So this is a class, so municipal and industrial conservation, where you almost always do it, and you always do it soon. A big box is you do it soon. Okay? So those are things that this contentious group, I always use the line, Mark Twain says, whiskey's for drinking, water's for fighting, right? So, so these are all things we can all agree we do now. Here are things which you sometimes do, but sometimes don't. Okay, but even if we do them, we never do them until later. Okay, in this case, about 20 years out. So we can all agree that, we can agree to disagree about whether or not we need to do these, but we can agree that, we don't need to do them now. And then there are things, a subset of things where you sometimes do those, sometimes not. If you do them, you tend to do them now. And so we can argue about those. But so what we've done is we've taken this, we've taken this very complicated problem and we've parsed down the set of portfolios into things we can agree to do now, things we can agree that we may or may not do later, and then things we can still fight about. Okay, and so, just to summarize this one, again, we just gave it a huge set of climate traces from a whole bunch of different sources, and we came up with a whole bunch of high confidence things you can say in a situation where people have a lot of incentive to disagree with one another. Okay, so let me go to some of the questions I think this raises. So first off, what is a good decision? When we talk about decision support, we say we're trying to improve decisions, make decisions better. So the first thing you can say is good outcome is not a good decision. Anybody have teenagers that they've raised? That's it. Right? Okay, so sometimes you do stupid things and it works out okay, and sometimes you do the right thing and it doesn't work out so well. So what's a good decision? In our chapter of the IPCC Working Group 2, we wrote about good decisions for about 2 years, and we said, we better come up with some criteria. So this is what we came up with. And so a lot of it is process-based. This is process-based. This is sort of the process, the global process. This is basically what's in people's heads. I want to focus a little bit on these two now, using the best available science and contemplating the decision from a wide range of views and vantages. So this is going back to my colleague Steve Bankus. So what's rigor and exploratory modeling? We can't validate the model. What's rigorous? So, he came up with this idea of, okay, you're really thinking of the computational machinery as lab equipment. So you want it to be doing what you think it's doing. I became my degree is in theoretical physics, and I became, in part went there by trying to measure, what was I trying to measure? Some physical constant in freshman lab. And it turned out I was measuring the disturbance by the Xerox machine in the next room. So you have to know what you're measuring. So the model has got to be working. It's not surprising because bugs, but it needs to accurately, reflect the consequences of your assumptions. So it can be calibrated, verified, but not validated. And to make valid arguments, so if something is true for all members of the ensemble, it'll be true as the world as well. So if you're going to constrain things, based on things that you have high confidence in the ensemble, that ought to be, reflective of the world. Properties of the ensemble are representative sample as a whole. So, and you need to be really explicit about, why you've defined the ensemble the way you have and how you've sampled it. But Steve wrote this like 20 years ago. So I want to, I put the other in it. But, what are the requirements for using information in this sort of analysis? Okay, which I think we started to touch in some of the conversations earlier on, but I think people if you kind of step away, that these models aren't meant to be predictive, but the models are meant to make better decisions and be the best available science you bring into this sort of analysis, be interesting to try to think about what are the criteria. So let me add one more complication, which is, this is a title of a paper we wrote, is it ethical to use a single probability density function? And I've gotten really interested in a whole body of work, which I kind of get into through Amartya Sen's book on the idea of justice, which is his answer to Rawls. And this is my one slide summary of this very complicated set of arguments, but essentially he says, an ethical reasoning about how we should act in the world needs to recognize that a diversity of priorities, goals, and values is an absolutely fundamental attribute of the world. People believe different things, and that's actually a good. Okay? And that there's irreducible uncertainty regarding the consequences of our actions. Okay? And so then he distinguishes between he says, two sorts of reasoning, and this is where he's critiquing Rawls, which he calls relational and transcendental. So transcendental is you seek agreement on the vision of an ideally just world. Okay, so this is essentially the Rawls veil of ignorance and all. So we all agree what the ideally just world is, and from that we can use this as a guide. Once we know the destination, we can then use that to adjudicate on what we should do in the near term. And so Sen says, that is not possible, but it's neither necessary nor sufficient. Okay, because even if we can't really come to agreement on this transcendental goal, but even if we could, the world is sufficiently imperfect and the options in front of us are sufficiently imperfect that really doesn't tell us what we need to do in the near term anyway. And oh, by the way, you can differentiate between the justness and not of many near-term actions, even if you don't agree on where you're going. And so he calls this relational reasoning. So seeks agreement on 9 ideal options before us are more just than others. And this kind of looks to me a lot like a much more worked out framework of some of the analytics that we're showing. And he argues, and that this sort of reasoning needs to be ultimately adjudicated by public deliberation, and he's among other things, a social choice theorist. And he says this works better when you facilitate re-examination and iterative assessment. So it looks a lot like the loops I was drawing. Demands clear explication of reasoning, logic, and values. So interacting with models and data forces you to be explicit. I didn't really mean that, I meant that, right? And then this idea that you need to recognize open impartiality, that you need to accept legitimacy and importance of a wide range of views of others. So just last slide then is, this is the analytic part, but this predictive approaches, which we often have in our heads when we're thinking about what we're going to do with science and how we're going to form decision making, generally seeks to aggregate information to consolidative models, and we're going to predict something, and once we predict, then we can rank options. And that's, in some sense, rather limiting in what you can do with the science. And so this backwards analysis where we're really opens up, I think, the space of products we can use. So, we can have certainly consolidative models where you have them are great, but we have exploratory models. If we just know something about a piece of the system, that might be useful because we can use that to, if we know this particular spot's not going to get wet, say because it's on a hill, we can put our generator there, right? And it can take understanding that it can't get into the models either because for a set of meetings, and it can deal with imprecise information. But again, let me then raise, given this wide range of things that you can do, given the contextual nature of, essentially it's very contextual. The information used for this problem may be different than for the people down the road or in a different sector. What counts as best? Oh, and then this need to, have this open impartiality to accept, many different points of view, where some sense the science is a constraint on actions which are not well related to consequence, okay? So having said all those words, what really are the criteria of what we can admit into this? What are the reasons for admitting certain information into it or not? What do we regard as, plausible? I mean, what are the rules? What's the frameworks for thinking about scientific information in this sort of argument?
Yes.
So I'm trying to work out what role these exploratory models are actually playing. And so I'll describe how I'm thinking about it.
Okay.
It might be the wrong way.
Okay.
And so I'll just be thinking about it in terms of super simple basic decision making.
Yeah.
And so you need outcomes, which are going to be a combination of the strategy and the climate scenario,
Yeah.
and you need probabilities. The first thing I thought was, well, we might think that if you're doing these consolidation models, these predictive ones, they're trying to give us the probabilities of the climate scenarios.
Yeah.
And you're like, nope, we're not doing that, we're
Right.
doing something else.
Yeah. Yeah.
So it sounds like you were saying what these exploratory models are doing is they're giving us something like the outcomes in some way. And then I thought, well, hang on. If the rubber just doesn't hit the road for these models, if these models just aren't valid, there's no external validity to these models, they're not surely telling me what the relationship is between the strategy and the climate scenario, because I don't know what's going to happen if I adopt that strategy under that climate scenario, right? I'm still missing important probability. And so the question is something like, sure, you can use models to generate scenarios, but use lots of different ways that you might go about systematically generating scenarios. I can just sit some people down and get them to make some stuff up.
Yeah.
If these things just aren't validated in any sense, if I've got no reason to think these track the world, then it seems like, in terms of basic decision theory, I should just say, well, either you're getting probabilities, if we're under deep uncertainty, either you're getting probabilities from somewhere magic, right? Or I'm worried that you're giving me this highly complicated, fancy-looking decision-making process that somehow gets these probabilities from somewhere, but actually you've said from the start, this gives us no guide to the way the world is, right?
Yeah.
So what role is this exploration actually doing, and where are these probabilities coming from? Because I feel like you're pulling a rabbit out of the hat.
Okay, yeah, great question. So let me actually go back to this slide right here. Okay, so, and let me tease out two things. So one statement you said, you're really focused on the climate traces, and actually missing the whole thing, the whole content, certainly this one, is that this is a highly complicated, engineered, hydrologic basin. And I actually have a pretty good model of how that basin runs, okay? Which includes all sorts of things that water runs downhill, evaporative. So I have a really good model.
So there's not deep uncertainty there.
There's not deep uncertainty there. So what we've done is we've taken the thing that we understand really well, and then we played the what if game on that. So, and this is a correct statement. If the next 50 years follows this daily trajectory of temperature and precipitation, for each grid cell over this basin, then this is how the system's going to function. Okay, so the model tells us that. Okay, and and the model's useful because you couldn't do that in your head.
Sure.
Yeah. Okay. And then you were very focused on probabilities at the end. Okay. So, but that's, and in some ways, I think classic decision theory may be over focused on that too. So here's a whole list of things that we got to in this study without any need to talk about probabilities. Okay. So we help frame. We help them identify the statement. Where the system is vulnerable. So that map I showed you, and I'll give you caveats in a second. But the map I showed you says, if temperature, for the specific metric on the river, if temperature is 2 degrees or higher, and average precipitation over the next 50 years is any less than the 100-year average, okay, then this system's going to fail, okay? So that's a strong statement. It's no probabilistic statement to it, and so that turns out to be a useful statement for moving this group forward, okay? And again, the information content of that is this engineered model of the river system that we have high confidence in. Okay, so that's to say we can say high confidence thing. Now, and then I showed you different classes. We brought in hundreds of different options for how to respond to these vulnerabilities, and I sorted them into 3 classes: things we can all agree we do now, things that we can all agree we wait on, and then things we need to argue about. And the arguing about, we'll regard at some level some probabilistic information. So I didn't show you that part, right? So, but I've done a lot before I get to that part where we need to argue over the last little bits, okay? So that's that part, okay. So there is, however, if we go back to the sampling question, a sort of an unexamined strong part, which actually the net example, touches on, is that the variability, the important variability, in the climate models. The reason we use a climate model as opposed to just scaling temperature up and down and precipitation up and down is because, the correlations, spatial correlations and temporal correlations matter a lot. And they're strong. I mean, it rains and snows in some parts of the year in this part of the world and it doesn't rain in other parts. And if it rains here, it might not rain here. I mean, so each of these trajectories has got a very particular spatial and temporal correlation. And we're implicitly assuming that this big ensemble of 2,000 different climate traces, okay, captures a significant range of that variation. All right, and so we could argue, we could think about that, whether it does or not. And clearly, in the Met case, I was actually joking with this. The guy we did this for on the phone last week. I mean, they've drawn more water, he said, out of Southern California's reservoirs this year than is left. Okay, and that's because we're down 40%. And so far because we're looking at 40-year averages or 20-year, 30-year averages in that model. So far, the trace that we've played out since the plan was done is still in the green. Okay, and that analysis didn't explore, near-term megadroughts. So that wasn't in our ensemble of 12, and so that picture doesn't capture the particular deep spike if it persists for another year or two. So. It's sort of a long answer, but I think, yeah.
So we have another question
Oh.
from Eric, and then
Okay.
Roman, if that's okay.
Sure, yeah. I'll let you do the questions.
So Eric.
My question is about when you have multiple objectives like that.
Yeah.
Do you find that it helps in somehow perhaps finding the right kind of the right scenario, or is it so? If you have only one objective, maybe you have multiple scenarios that will meet that objective.
Mm-hmm.
If you multiple the objectives, does it narrow the number of scenarios that you could actually and making the decision process easier in a sense, or? It's just an intuition.
Yeah. So first off, a linguistic thing is that we tend to use scenario for a state of the world, for characteristics of states of the world, and then strategy for an action you take. Though sometimes people use it the other way. Yeah. So, but anyway, so I'll interpret. I think you meant what we would call a strategy.
Yes.
Yeah. Okay. So the claim is that if you have multiple objectives, there may be fewer strategies. Maybe, but it might also be that the trade-offs are tougher, so that you've got sort of a wider trade-off space, and that there's just another dimension of things that you need to confront. So that if it's a single objective, there might be sort of a small region which is good, unambiguously good compared to the others, and with multiple trade-offs. I mean, like in the Colorado thing, I didn't go into that, but the picture I showed you was for one portfolio of options, and we actually looked at 4. One focused on environment, one focused on cost, one focused on everything, and one that was sort of a blend of environment and cost. And I showed you, I think, the one that was focused on everything. But there's a reliability, environment, cost trade-off, which adding the multiple dimensions adds to that. So you essentially need to do that analysis for along the whole cost spectrum. And so that, I think, there it complicates the answer.
Okay.
Yeah. So not necessarily. Yeah.
Changes
Though actually in the one I showed you with the fancy algorithm with the cube that went around, that I think fundamentally it simplified it, looking at multiple objectives and going to the robust. Looking at multiple objectives under deep uncertainty actually simplified it because you got rid of all the complexity of the decision space, which were the complicated markets, and you really just need a simple market, because that's the only thing that's robust to go over all these objectives, over all the uncertainties. So I think I have an example of both, and no sense at all how to generalize the 2 points to Anne.
Roman has got the next question.
Yeah, I just wonder whether you could say a bit more about how you handle the scenarios. This went very quick. At some point you said you needed to find a probability threshold for decision making with scenarios. I wonder if you could say a bit more about what sort of decision rules you apply to these sort of scenarios of scenarios.
Yeah.
And then following up on the first question, where do you get the probabilities from? So what methods do you use to define these probabilities? You said, well, you can integrate your function over various probability functions. Then the question becomes, how do you narrow down from the set of probability functions that you consider in these modeling calculations?
Okay, yeah, so we get the scenarios, and again, let me sort of lay out some terminology, let me use the word case, which I was using a little loosely in the Colorado example, but a case is one policy in one future. So a future is is a parameter that describes a future state of the world, and then a policy, a strategy, and a future is a case. Okay, so if I look over a whole bunch of futures, a scenario is a group of futures that share a certain set of characteristics, like this policy works or doesn't in that. So that's what I mean by scenarios. So the way we find those scenarios is running the model a bunch of times, specifying a criteria for what counts as a future that's in or out of the scenario, and then doing this classification cluster analysis to find a simple description that people can understand. Okay, so that's where the scenarios come from. And first said was similar to the answer over the question over there, is that even without probabilities, that scenario can be useful because it helps people understand the vulnerability. Okay, so the point about the probabilities is that the probabilities are, you need those when you need to adjudicate tradeoffs. If you were sufficiently confident that scenario would come to pass, you would do X, and if it's not, you would not. So that was essentially what this Port of LA thing was. And so the threshold is, you can calculate, you need to have some assumptions about basic distributions, but you can calculate that threshold. It's not a it's not a property of the world. It's not a property of the futures. It's a property of the strategy, essentially. Okay, so again, in the Port of LA, it's if you're risk neutral, and given the costs we assumed, that future, that scenario I showed you. Go back here. Okay, so this is our scenario, right? Okay, so the scenario says if sea level rises that rapid, the terminal lasts that long, and the change in storminess is that much, then if you knew that was going to happen for sure, you would pay the insurance to harden it the next upgrade. Okay, and if not, you wouldn't. And so you can take this this distribution of cases, and using some assumptions about what the distributions look like, you can say if 7%, if this is 7% likely, then and you're risk neutral, then it's worth paying the insurance. Okay, so that's a statement about the strategy and not the state of the world. Then what I did is I went through and I say, what probabilistic information do I have? Okay, and let me go to Tool. So if I estimated a probability range for this, but let's assume I knew what that was. Okay, then this is just math. Okay, if there's three conditions, and if the first condition is 16%, and the total, and you need that scenario needs to be 7% likely, this is what the other two conditions need to be, the probability, assuming that they're uncorrelated, in order for the scenario to have 7% likelihood. So again, this is what we're trying to do is show you things which are high confidence. Okay, then you can use this threshold and lay the information against it. So here we actually have no probabilistic information per se, and we just have these judgments. And so it's essentially, we give this threshold, and then people, the planners can make their judgment. Okay, this one, the upgrades occurred every 20 years, which suggests that a 50-year lifetime is pretty unlikely. However, it's contingent on they upgraded every 20 years because that's how fast container ship technology was changing. So the judgment about how long this one's going to last may depend on what they judge about technology. But at that point, it's just sort of expert, sort of Bayesian prior, right? And here we don't have very many studies, but virtually none of the studies. I mean, looking across all the studies of how this parameter changes, only one even gets into this region. So again, you take sort of a Bayesian expert. So at some level, it's just you look at the evidence and you make your the decision maker makes their judgment. If not, we're making it. Here, I went through a process where we try to estimate probabilities from existing science. But I think the simple answer to your question is we come up with a plot like this and then lay the available evidence against it. So if there are studies that have estimates of probabilities, you can lay this on here. I mean, ideally, you would like to choose, to fiddle with your strategy so you can get one where the threshold is far from the estimates. Gives you some safety margin.
So I did see some other hands up. Pareto has a question, but we are out of time here officially. So if we could carry on the conversation, we've got room out here. We've got the bar downstairs, and we'll be meeting at Asher's at 6:30. So please enjoy the rest of your time, and join me in thanking Rob for.
Thank you.